Hi, this is lecture number 9, and in this lecture we're talking about system identification. This is part 1 of 2-part. So here we are in this unit, and these are some of the topics we've talked about. And so now we're talking about the subject of system identification. So when it comes to system modeling, there are 2 methods we've been talking about. The first method is the analytical method. The analytical method uses, for example, the laws of physics, KVL, KCL, Ohm's law, all of those different device characteristics that we have equations for. And we actually write out the equations, and based on the equations, differential equations, algebraic equations, we end up with a model of a system. The other method that we would use is called the empirical method. The empirical method is a method that involves experimentation. So we have the 2 different methods. We've talked somewhat about the analytical method. So in that we've looked at modeling of electrical and mechanical systems. We've talked about the H transform and how it takes a discrete continuous time system and gives us a discrete time model. So in the method that we're going to look at now, the empirical method, in this method, it automatically gives you a sample data model of a system. So you don't actually have to use the H transform. It's kind of embedded in the entire process. So 2 different methods. So the important question is, how do we obtain a transfer function empirically? So in order to do this, we need to use a little detective work. We need to use the data that's available to us and basically obtain a model from that. So here is the approach we're going to take. The approach that we're going to take involves an arrangement like this. So this is the arrangement we used to perform the experiments that we're going to be doing that give us the model. So basically we start with an excitation signal that we apply to our system through a D to A converter. Okay, so that's important. The output of the system then is sampled by our A to D converter. We take both the input signal and the output signal in discrete time into something I called an identifier algorithm. And from that identifier algorithm, we get a model. So this is the approach that is used that we're going to use in terms of the experiment layout. So we basically use the connection of the system exactly the way we're going to use it. So in this case, we apply some kind of a signal to the input of our system. We compare the input and the output of our system and get a model. So that's the basic idea for this. So in this process, we have 4 steps that we're going to go through. First step is called experiment planning. Here we plan the experiment out. There are quite a number of details associated with planning the experiment. The second thing we're going to do is do the selection of model structure. These 2 steps together form what I call the paradigm for our system identification process. So once we've done that, then if we're going to do a parametric model, then we will do the parameter estimation, the estimation of the parameter. So for example, if we're looking for a transfer function, then we'll be looking for the coefficients of the numerator over the denominator. Okay, so those coefficients are parameters of our model. And so if we're seeking those, then we would estimate the parameters from the data that was obtained. Now, obviously, the way we obtain the data is going to have a big impact on how we do our parameter estimation. Finally, we have model validation. Model validation basically is a sanity check to see if what we've done makes any sense at all, or rather, if the results that we get are meaningful, useful. Okay, so it's a way of going back and checking to see if this whole thing was done in a way that actually makes sense, or whether or not the model is even usable. So by model validation, we will go back and check to see if it's even useful. Okay, and so we're going to have each of these steps requires sub steps associated with them, and so we're going to march through all of these steps. Experiment planning. First of all, how much data are we going to use? What sampling rate are we going to work with? Okay, so when we do this, to do the experiment, we have to pick a sampling rate to begin with? How do we know what sampling rate to pick? Well, that's not always obvious. Generally, you want the sampling rate to be related to the ultimate control problem that you want to use. So that is, you want the sample rate to be small enough to capture all the important transient characteristics that we're looking for, but not too small. Okay, we don't want it to be too small. So small enough, not too small. So there's definitely a range of useful values of sample rate, and so it's common just to start and just to pick one, just to pick something that makes sense for our system. So if your system moves really, really slowly, then a sampling rate of 1 second might be fine. If your system, for example, like in aircraft like autopilot and that kind of thing, those kind of controls use 20 millisecond sampling rate. Okay, so that's a very common sampling rate for an aircraft, 20 milliseconds, which is obviously a lot smaller than 1 second sampling rate, sample period. So then there's the type of excitation signal that we're going to use. What kind of a signal do we apply? Is a step input okay? A delta function? Sinusoid? What kind of a signal is really going to be useful for us? Okay, and so we'll talk about a lot of these characteristics, these details of the experiment. Availability and use of a priori data. So what does that mean? Well, for example, a motor. You're turning a motor. If you apply voltage to the motor, and the motor will turn, obviously. If you turn off the voltage, the motor does not return to its original state after you turn the motor off. In other words, it doesn't. So when you apply voltage, the motor turns, right? And then when you take away the voltage, it doesn't turn back. Okay, and that it sounds like, why would it turn back? Well, obviously a motor won't turn back, so that's important. That characteristic of applying a voltage, having the motor turn and then not going back after you release the voltage, that corresponds to a particular characteristic of a system. That is, the system has a free integrator in the system. That is, the denominator of the system can be factored in the Laplace domain, can be factored and have an S term by itself in the denominator. Okay, so that fact is an important fact in working with the motor. Okay, that's a priori data. We know that ahead of time, and so we can actually incorporate that data into our model when we work with the model to obtain the model parameters. What about available resources? Available resources, for example, what computer is available to us? What kind of calculations are we going to do? In other words, are we going to try to do this system identification using MATLAB on a PC, or are we going to try to do this on an Arduino? What exactly are we looking for? What are the resources we have available to us? Also, online or offline computation. Are we going to try to obtain a model while the system is on operation? That's the online. Or offline. That is, we collect a bunch of data and then shut the system down and process that data and get a model from that. So those are two different methods, and of course that will definitely affect the type of experiments that you work with. Finally, pre-stabilization. Is our system initially unstable? If so, trying to do system identification with the diagram that I just showed will not work, because the system will blow up, and that's not a good thing. Okay, so we may need a controller to pre-stabilize the system, and so we actually identify not the actual system, but a stabilized version of that system. And then how does that stabilization include? How does that affect the results that you get when you're all done? So these are important issues that we need to address in the experiment planning. Okay, the hypothesis is the selection of model structure. So when you think of an experiment, whenever you're doing experiment, it's important to have a hypothesis. In other words, what is it we're setting out to prove, one way or the other? Okay, so a lot of what you're learning in this lecture is about empiricism, and that is, how do we actually proceed and approach the problem of trying to obtain a model? Well, in a sense, you already need some idea of what you're looking for, and based on what you're looking for, then you can perform an experiment to help you see if, to see that characteristic, that behavior. So that's what we're looking for when we look at the selection of the model structure. So first of all, we want to incorporate prior knowledge. What knowledge do we have prior? So I talked about the integrator, for example. Does the system have an integrator? If so, then we want to incorporate that into our model. So we can assume, for example, no prior knowledge. So we're starting from scratch, assuming nothing about the system, in which case our system is considered a black box. Okay, it's considered a black box. Black meaning no knowledge about that, no light there. So, or suppose you have some prior knowledge, in which case the system is a gray box. It's not completely black, it's gray. You've got a little bit of light in there, and so those are two different things to think about in terms of the model structure. So if we already know something about the model structure, then we want to incorporate that. That's our gray box. But if we just assume nothing about our system, or very little about our system, then we would start with a black box. What kind of model are we looking for? A parametric model, for example, a transfer function, is that what we're looking for? Or are we looking for a non-parametric model, for example, a Bode plot, okay, or a Nyquist plot? So these are two different types of models that we may be looking for. And actually, when we do the system identification process, we're primarily looking for a parametric model. However, we will also use a non-parametric model to evaluate the parametric model. So that when we talk about the model validation, that's one of the things we'll be using to validate the system. We'll actually do both types and compare them and see how they compare. If they don't compare, well, that's probably there's something behind that, and we need to check into that. In terms of the model structure, we're thinking, for example, of a transfer function. So are we looking at a particular order of our transfer function? Are we looking at a second order model, third order model? What order of transfer function? That's important in the selection of the model structure. Also, the relative degree. Are we expecting a particular relative degree? So remember, the relative degree is the order of the numerator divided by the order of the denominator. Are we expecting a particular relative degree? And if so, then we may need to incorporate that into our model structure. So that's our model structure. We're generally going to be assuming a transfer function that we're looking for. We're going to fix the order to be some number, second order, third order, whatever, and then we'll proceed from there. So having fixed now our model structure, we perform an experiment, we get some data. Now what do we do with that data? Well, we have a model structure that we're looking at, and if we're looking for a parametric model, for example, a transfer function, then we're looking for the coefficients of the numerator and denominator. So now we have a model, we have data. How do we get the parameters of that model to fit the data? Okay, and so that's this subject of parameter estimation. That is, we're seeking to find the best values for a given parameterization. So if we have a third order transfer function, for example, that's our parameterization. What are the coefficients? What are the best coefficients for a given parameterization? So in order to determine what best means, we have to have a way of evaluating good versus not good in a model. And so we would select an appropriate cost function we want to minimize. For example, least squares. The squares would be the cost. Least squares means we're trying to minimize that cost. Okay, so in general, we talk about this in terms of cost because we have the general thought that high cost is not good while low cost is good. Okay, and so we generally will take this and cast it as a standard optimization problem, for example, a least squares problem, and then solve that. So this is the approach that we will take towards parameter estimation. And again, we're just marching right through the 4 steps of the system identification process in general, in little detail, very little detail, but kind of addressing the important issues here. We're going to go back later, and then we're going to actually look and see how to actually do these things. Model validation, again, is the sanity check of the system identification process. Is what we came up with even worthwhile? Second, does the obtained model actually fit the data? Okay, so we for example, we'll go through the parameter optimization and we'll get a set of parameters. That basically is a numerical transfer function that we will get. Does that transfer function actually fit the data? Maybe it does, maybe it doesn't. We're going to find some things that can cause it to not fit the data. So some tests then will need to be run to validate the model. Okay, so it's very common to have data that's generated from an experiment that's used to do the parameter estimation, then use a different set of data to actually do the validation to see if it works on different data, not just the original data. Okay, so that's important. So ideally, such tests should be independent of the data used to obtain the fit. So that's what I was just talking about. Tests should also, the tests that we run for model validation should be in the domain of fit as well as alternate domains. So what are we talking about here? Okay, so we're going to obtain the data from our experiment in the time domain. Okay, that's how we're going to mostly. Actually, we're going to look at a couple different methods. We're going to actually look at time domain. We're also going to look at frequency domain. Okay, but in the time domain, then, if we take our data in the time domain, then we can compare the transfer functions in the alternate domain, which would be the frequency domain. Okay, so that's what we're talking about when I talk about alternate domains, time domain versus frequency domain. Okay, so let's look at a couple of introductory examples. So here's our first introductory example. Again, we have our configuration set up, and I apply a sequence of values to our input. Okay, so basically you can see this is just an alternating sequence, 1 minus 1, 1 minus 1 sequence. And we apply this data to to a system, and out comes this data. So we get these values coming out of our system when we apply these values. So k is the time variable. In this case, we're only choosing 5 values, so it's not a lot of data. But this is just to kind of help you see some of the process that we're going to go through. So here's the data that we get. And we're going to start with this hypothesis. I'm going to assume a first order system, okay, that is strictly proper. Strictly proper in this case means the denominator evaluated at q equals 0 is 1, and the numerator evaluated at q equals 0 is 0. Okay, that's a strictly proper system. So this is a first order strictly proper transfer function. We're looking to find the values of A1 and B1. Those are the parameters for this model. Okay, in this case we have 2 parameters. We have 5 pieces of data, 2 parameters. Okay, and so we're going to try to find the A1 and B1 that best fit the data. And when we say best fit, we mean in terms of least squares. So this transfer function, if we have output y and input u, corresponds to this difference equation. Okay, so when we look back at difference equations, there was a direct relationship between a transfer function and a difference equation. So this is the difference equation that we get from this transfer function. Okay, and so what we're going to do then is we're going to use the available data. This is our hypothesis now in the time domain. Okay, so this is our hypothesis, and that's why we need to go to this, because our data is in the time domain. And so now I want to use the data with this hypothesis to evaluate the, just try to solve for the unknown coefficients A1 and B1. Okay, so I'm going to stack the data from 1 to 4, y1, y2, y3, and y4. If this actually, if the coefficients A1 and B1 exactly define the model, then we actually get equality here. Okay, so y1 would be equal to minus a1 y0 plus b1 u0. y2 is equal to minus, so that's just, again, this difference equation where I let k equal 1, 2, 3, and 4. Okay, and again, I just stack the equations together. So notice a1 always appears in this column, b1 always appears in this column. We can factor that out this way, a1. So I have this matrix times this column gives this vector. Okay, so this a1 multiplies the elements in this column. B1 multiplies the elements in this column, and so we get this situation going. Now, in this case, we know the y values, and we know the u values, and so we have a linear equation. Okay, we have a linear equation. We can write it this way. Y is equal to x times theta. Theta is our set of parameters, and I use theta here only because it's very common in the literature for system identification, not because I want to confuse you using Greek letters. It's all Greek to me. But so anyway, we have this linear equation. Y is given by this. So again, y here is associated with the values here, y1 to y4. We just plug those values right in, and we get this vector. X here is this matrix. And so again, we plug the values of y and u in, and we get x. Okay, so here's y values. Here are u values. Actually, these are minus y values. These are u values. Notice that these are shifted and negated. So that's, again, from this difference equation, we got that. And so our theta is our set of unknowns. So this is known, this is known, this is unknown. Okay, and so we're going to solve for that. And to solve for that now, we have more equations than we have unknowns. That is, we have an overdetermined problem. The least square solution to this overdetermined problem is the pseudo-inverse of x times y. In this case, the pseudo-inverse of x is equal to x transpose x inverse x transpose. And in general, this is the form that we're going to be using when we do the least squares method, because we will generally always want more data, more equations than we have unknowns. And again, that's because we're trying to fit the data, and our data itself may be noisy, so there's no single value that we know is absolutely right, and so we have to work with that fact. So this is the way we're going to do it. So this is pretty much always going to be the pseudo-inverse form that we're going to be using in this case, because of the fact that our X matrix is always going to be tall and thin. Okay, and what that is, we have a lot more equations than we have unknowns. So the equations is the number of rows, the unknowns corresponds to the number of columns, and we will pretty much always have that. So in this case, X transpose X is going to be given by this. X transpose Y is given by this from those matrices that we had before. And so when I take the inverse of this times this, I get this. And so now this is A1, this is B1. So B1 went in the numerator, A1 went in the denominator. And so we have this, this is our model now. So we have taken an experimental data, we have applied it using the hypothesis, and now we obtained a parameter, we optimize the parameters of our model, and so this is the model that we obtain from the process that we've done so far. So we now have a tool for obtaining a transfer function from data. Cool. Ooh, yeah. All right. So this example illustrates two parts of this process. It illustrates the selection of a model structure and illustrates the parameter estimation. So those are important things, and those are the parts that actually make us feel good about this, that we can take data and actually get a parameterization for that. Okay, so we haven't really, this didn't illustrate much about experiment planning or model validation, the process of that. Okay, here's the second example. Here's some other data. We apply this sequence of values. It's like, where did that sequence even come from? We apply the sequence of values, and we get this sequence of outputs. Okay, notice that in general we will not get nice integer values to work with. Generally, it's, we get messy stuff. Okay, so here is our hypothesis that we're going to use for this problem. It's a second order transfer function. It has unknown coefficients A1 and A2, B1 and B2, second order. So we're going to try to find the best values of A1 and A2 such that the data fits this model. Okay, so that's what we're looking for. So associated with this model is this difference equation. So notice that here I'm assuming a negative sign. Okay, it turns out that that's very common when you look at, for example, when you look at the Laplace the Q transform of various signals. it's very common to have a negative sign here. So we're going to assume that it's a negative sign here in our model. And so if in fact the sign is negative, then this coefficient will be positive. So that's all this is doing. It turns out that when you go through the system identification process, if you assume that this is positive, and it's supposed to be negative, it'll come out to be negative. So it doesn't really matter if you put the signs in, but this is just to kind of illustrate what we're looking for. So we're looking at the values a1, a2, b1, b2, and this transfer function is related to this difference equation. There's a one-to-one relationship, and actually we could assume this difference equation as our hypothesis. Instead of the transfer function as our hypothesis, we could have assumed the difference equation as our hypothesis. They're equivalent, and so we could choose one or the other. So notice that this negative sign corresponds to this being positive. This positive sign corresponds to this being negative in the way the difference equation is formed. So that's our hypothesis, and now we can take the data and use this hypothesis to stack this data. Okay, so we're going to stack it from k equals 2 to 9, and this is what we get. This is similar to what we did before. Okay, so this row times this column basically gives that difference equation at k equals 2. Now, why do we start at k equals 2 instead of k equals 1 or k equals 0? Well, the reason is that in this difference equation, I assume that I only have knowledge of data of y and u from time 0 on. Okay, and so this, when k is equal to 2, we get k equals 0 here. I mean, this becomes 0, this becomes 1, this becomes 2. If I were to choose k equals 1, for example, that would require knowing y at time -1, so I can't assume that. So I'm going to assume that k goes from 2 on. So in our case, we have from 2 up to 9 available to us, and so I stack that data. So notice that here I get positive signs, here I get negative signs because of our hypothesis. Okay, and so we've stacked the data into a matrix equation like we did before, and now we want to solve this matrix equation. So again, we can write this as y is equal to x times theta. X transpose x comes out to be this, x transpose y comes out to be that. The pseudo-inverse then, when we solve it, gives us this. This then gives us the transfer function. So these are the parameters that we solve for. These are our best parameters, theta star. And so this gives us this transfer function. So we've gone through a couple of examples. Now let's look at the general solution to this problem. In the general solution, we have n data points. Okay, so we go from 0 to n-1. That's capital N data points. So we apply this sequence of values u from time 0 to n-1. We obtain these values y from 0 to n-1. So we have data. Okay, we have data. Next, we assume a parametric model. We're going to assume a transfer function of this form. Okay, so in this transfer function, we have a monic polynomial in the denominator. In this case, that means when we evaluate the polynomial at 0, we get 1. When we evaluate the numerator at 0, we get 0. So we're going to assume that as part of our hypothesis. We're going to assume that our plant is strictly proper, and we're going to look for coefficients b1 to bm and coefficients a1 to an. So that I have n coefficients in the denominator, m coefficients in the numerator. These two might not be the same, and so we kind of keep it general that way. So this is the model that we're going to look at. This model, this transfer function, is related to this difference equation, either this form or this form. Okay, and so we're going to, again, we could have started with this as our hypothesis, but we know there's a direct relationship between the transfer function and the difference equation. Now I'm going to take this equation and I'm going to factor out the unknowns, this side of the equation. When I do that, this is what I get. I get this row times this column. So this column has all the unknowns in it. And then this is going to be a value that's known, and then I have a vector here that's a row vector that's unknown. So I'm going to take my data and I'm going to stack it. Remember, I have n data points. Okay. Notice that I'm going to want to start it at whenever this is equal to 0. So this is the smallest, the earliest value of y, earliest value of u. So whichever is larger of n and m, I'm going to start with k to be that. In general, we'll have n be the larger, but it could be the other way around. So for now, we're going to assume that n is larger, but again, it doesn't matter. We could easily switch around the other way. Okay, so we're going to define for L now. We're going to stack L minus n rows into this matrix. Okay, so L minus n rows. And so this is what we get when we stack the data into rows. So this is the rows in X, this is the values in Y, and again, we still have our parameter vector that's unknown we're going to try to solve for. So again, we get this equation, and if we use all of our data, that is when L is equal to n, then we have yn xn times phi. So we have our known data, we have our unknown data, we can solve the linear algebra problem, and again, we get the least square solution. The optimal set of parameters is given by the pseudo-inverse of x times y. So here's the pseudo-inverse of x transpose x inverse, x transpose y. And so we have the optimization of parameters for this problem. So having solved the linear algebra problem, we're able to come here. So we've talked now about the two parts, the model selection and the parameter estimation. Now let's back up and talk about experiment planning. So experiment planning is part of the system identification process. It's the first step in the system identification process. So in experiment planning, first thing we need to look at, or first thing we're going to look at, is the excitation signal. The excitation signal needs to be sufficiently rich. That means it needs to be exciting. It needs to be woohoo exciting to the system. So in particular, it needs to be at least on the order of the model to be fit. That's like the minimum requirement. But in general, we want a high order excitation signal. The signal that's needed is needed to excite the system in all its nooks and crannies. So if our system has, for example, a resonant peak, then we want to be able to have a signal that has a strong component at that frequency and so forth. Or a notch. If we had a notch, we want to be able to identify that notch. So in particular, the signal should not cause the system to either blow up, that's not good, or enter into a nonlinear regime. Okay, we'll talk more about this nonlinear regime when we come back to the problem of robust system identification in the next lecture. So we'll come back to this guy. Also, the signal should contain enough data values to provide a good fit. In general, the more data, the better. Okay. So what is this deal about the order of the signal? What is the order of the signal? So the order of the signal is the greater of the order of numerator or denominator of the signal. So example, these two signals in the Q domain are first order signals. This is a step input. This is a signal that alternates plus and minus 1. And these are first order signals. Here is a second order signal. This is actually the Q transform for a sinusoid. So even though the sinusoid is continually moving, it's moving in such a rhythmic fashion, it only counts as a second order signal. For higher order signals, we can consider something like a chirp signal, sometimes called an FM, frequency modulation. This is a sinusoid where the frequency of the sinusoid keeps changing. In this case, it keeps increasing. This will, if you were to take the Q transform of a sampled version of this signal, you would generally get a high order rational function out of it. If we look at the frequency response of this signal, we basically get a signal that's flat out to a certain frequency, okay, and then it drops off after that. But it's fairly flat. So the idea flat is good. That means you're considering all frequencies roughly the same. So at least in that region, all the frequencies are roughly the same. That's pretty good. Another signal that has a flat frequency characteristic is the sync signal. It's flat out to a certain frequency, and then it drops off after that. So if you remember, a true sync function that goes from minus infinity to infinity actually has a frequency domain that's a square, a box, right? And so here, it's almost a box, and that's because we don't go all the way out to minus infinity and go to infinity. Here, we're going to stop at some point. And so because of that stoppage, we get this happening. So, but what's important is that it's flat out to a certain frequency. Now, it turns out that the sinc function is such that if you take the sinc function and compress it in time, that basically expands the frequency response out. So I could actually expand this frequency response all the way out to the Nyquist frequency by compressing this sinc function down. But the problem is when we sample that sinc function that's compressed down, if we compress it all the way down, we'll basically get something like a delta function. We'll have 1 at this value and then zeros everywhere else. And that's a very simple function to implement. You just have all zeros and then a 1 and then all zeros. Very simple to implement. However, when it comes to identifying systems with a lot of noise, so for example, your system, the sensor that you're actually using to measure the output could have noise associated with it. That noise is going to be create problems if you're applying an excitation signal that's all zeros and a 1. Okay, so it turns out that's a problem. So in theory, this would make a really good system identification excitation signal, but in practice, not so much. Another rich signal is a multi-sign. So multi-sign is basically a signal that's a sum of sinusoids of various frequencies. Okay, and the frequencies are basically give us these little peaky values in our frequency domain. So it's peaky at various sine frequencies that you add, at the specific sine frequencies that you add together. So the value of the multi-sign is that it gives you peaks which allow you to accurately represent or identify the system at those peak values. So if there's a particular feature we're looking for example, a resonance or a notch, then we would want to apply a sinusoid at that frequency just to get to be able to identify that well. Another very important rich excitation signal is a random binary sequence. And if you were to plot a random binary sequence, this is what it looks like. It's either +1 or -1, and it switches. And so since the function is actually either +1 or -1, you don't actually see any transitions between the two. And so you just get what would look like a line and a line. And so the frequency response of that looks something like this. Notice that it's noisy. It's very noisy, which means you have very high values of the frequency response and also very low values of the frequency response. So, but it turns out because what we're identifying is a rational function, the rational function can't change that quickly in terms of its smoothness. And so turns out this is actually a really good signal. It's fairly easy to generate. We'll come back later and see how to generate a random binary sequence. But this is an important signal for us. And as you can see, the frequency content goes all the way out to the Nyquist frequency. Now, what about excitation for marginally stable systems? One of the things we said is if our system is marginally stable. Okay, so for systems that are marginally stable, that is, we don't want our system to blow up while we're doing the system identification process. So for systems that are marginally stable, care must be taken. So again, marginally stable has, in Laplace transform, poles on the imaginary axis. And the reason is that if you have poles on the imaginary axis, a bounded input can give an unbounded output. That is, the output can blow up. And that may not be a good thing. Okay. For some signals, for some systems, that's not necessarily a bad thing, but it can still come back and bite you. So you just have to be careful. So a rich signal can generally be found that doesn't cause the system to blow up. So here's an example of a signal. I call it a modified chirp. So notice it has a chirp component in there, but then it also has like this pulse up and pulse down that's attached to it. And then I take this whole thing and I turn it upside down and I apply it again. Okay, so this half is the negative of this half. And so what happens then is when you apply this part of the signal, your system may meander off. And then when you apply this version, it meanders back. So it doesn't go too far away. However far it goes, in this part, it'll come back in this part. So another example of a random sequence. So a random binary sequence can be obtained by taking a random sequence like a band-limited white noise, putting it through a sine function. So again, the sine function, if this signal is positive, it will give a 1. If the signal is negative, it'll give a -1. And so that is how to generate a random binary sequence. But now we're going to take this signal and subtract this signal from it. This is a transport delay, is a time delay. So we're going to take the same signal. So whatever signal this is, we're going to apply it to the system. Then we're going to take that same signal and we're going to subtract it sometime later. So basically what happens is this signal is constantly having a random sequence applied, and we're also having its negative applied. So the result is that the system with a pole at the origin will not drift off too far. It will still drift, but it won't drift off very far. Okay, so this is important. So this is these are some rich excitation signals, and we'll use these. We'll actually use this one quite a bit because one of the systems we're going to be doing a lot of system identification experiments with is a motor, which has a pole at the origin. So this is why we would use this particular one. So how much data? So this is part of our experiment planning. How much data? In general, the more the better. We're obviously limited by computer power or memory, but I have to say that things have changed a lot since I first started teaching this class. When I was teaching this class, the first time I taught this, I was teaching this on the students were using an IBM PC. This is even before the Pentium days. 386 computer, 286 computer. It's like, do you guys even know what that is? And I think maybe we had a few megs of RAM. Megs? Yeah, megs. So things have come a long way. And so what was once a lot of data, for example, 2 to the 14 data points, 16,000 data points, what seemed like a lot of data now is like, it's not that big of a deal. And the computation power required to do it, we would use 2 to the 14, and that's a great number. That's a significantly large number. And it used to be we'd have to wait for the result. Now there's really pretty much no waiting. So how much data? Well, data is not as big of an issue as it was in days past. So next we come to the subject of model validation. In model validation, which is the fourth part of our system identification process, we have the question, again, it's the sanity check. So how do we validate our system? Well, practically speaking, as I mentioned, we're going to want to use alternate domains. So our data is collected in the time domain, and so the frequency domain is an alternate way of looking at the data. So because they're alternate domains, it's basically taking the same data and looking at it in a different way. And if by comparison, if things compare well in the frequency domain, that's a pretty good way of evaluating whether it's a good fit. So the FFT basically takes a sampled signal, gives an approximate Fourier version of that signal. So we've seen that already. This can be used to obtain the alternate perspective on the system. So what we're looking for in this frequency domain approach is a non-parametric model of the system that can be compared with the outcome of the system identification process. Okay, and so this is what we're working with. Okay, so we have a signal that we sample. We're going to take the signal, we're going to sample it, put it through our FFT, we're going to get a signal out. Okay, and so in general, our frequencies will go all the way out to pi over t, the Nyquist frequency. Okay, and so that's what we're going to be looking at here. So here I plotted u e to the minus j omega t. Remember that the Laplace transform of this signal, if we were to plot it, we would actually have to put a t out front, the sampling time out front. And of course, multiplying by the sampling time is in general going to change the magnitude. So that's a big deal. It's an issue. when you take a set of n values, for example, n is equal to 2 to the power L, n values, and you take the FFT. So here, this is in time domain. This is now in frequency domain. These are the actual frequency values you get. We get e to the j0 all the way up to e to the j 2 pi n minus 1 divided by n. So this, if n is large, this is almost 1. So it's like frequency j0 to j2 pi. Okay, so basically, these e to the j values basically are equally spaced values around the unit circle. Okay, equally spaced around the unit circle. Now it turns out that what happens on the top half of the unit circle, the bottom half of the unit circle is the conjugate of the top half. And so in terms of magnitude, there's it's like a mirror image of what happens. And so we only need to use half of this data. So basically we take this data, we convert it into the frequency domain, and we only use half of this data in evaluating the frequency response. So here's what we do in order to obtain a non-parametric model using the FFT. We first perform the FFT on both input and output. We obtain the input-output ratio of that data. This gives us an estimate of the frequency response of the system. This estimate can be used to obtain a Bode plot, that is, a non-parametric model. So in terms of a block diagram, we take our system, we apply our input, we sample our output, we put both of these into an FFT, both of these signals, divide this signal by this signal, and that gives us an estimate of our transfer function. Okay, that gives us an estimate of our transfer function. So here's an example of the kind of thing that we could get. Okay, so here's a system that we have, and we have multiple orders. We have the actual system, we have a second order model, third order model, fourth order model, and then we have the data. So the data here is what we get from our FFT. Okay, we take the FFT of y, FFT of u, divide the two, and we get the this, and we can plot that as an FRD. Okay, and so that's what this orangish color is, yellowish color. So we have these responses. So our actual system, notice, goes down here like this. The second order model, notice that this system has a resonance here. The second order model has a resonance, but first of all, this initial data out here is not very close. This data out here at high frequencies is not very close. So the data for the second order model, this shows us the second order model is not a good approximation of our system. So if we just did a second order system identification with this, we would not have a good model. Okay, so this green, which is there's an orange and a green here, and notice that both the orange and the green lie pretty well on top of the actual transfer function. And so out here at low frequencies, we see that in fact we get, there's a divergence that happens. But keep in mind that what's happening down here, these values are very small, 10 to the minus 5, compared to, for example, these values over here. So, they're 10,000 times smaller than what's going on even right here. And so this is insignificant. And so really what we can see now is that the third order model, so in other words, we used actually 3 different hypotheses: second order model, third order model, fourth order model. The third order model, we can see, actually fits the data well. And so using the principle of parsimony, that is, the principle of keeping things as simple as possible, in this case would mean we would choose the third order model as our model. Okay, we would not go to the fourth order model, and so we'll actually see why when we do this. But this then is the example that we have. So this is an example for some data, and in this case we actually use quite a lot of data, like 2 to the 14 data points. I'm not bothering to show you all those data points because it's just like a lot of numbers. You don't need to see all those numbers. Okay, but what we can see is that by trying the different hypotheses, we can actually, and again, the calculations, once you have your problem set up, the calculations are very straightforward to do. And so we can easily do the second order model, third order model, fourth order model for these systems, for this data. Okay, and as we can see, it works pretty well. It does not work well for second order, which means the second order model is not good, but it does work well for the third order, fourth order model. And it actually, the second and third, the third and the fourth actually fit the actual data, the actual transfer function well. And notice that the data actually fits the transfer function fairly well out till about this point. And then after this, we say that it gets lost in the noise. Okay, so you can see the signal is very noisy, and what happens is that the signal gets lost in the noise. So we have things like what's called a signal to noise ratio. That is, there's a certain amount of noise there, and if the signal to noise ratio is too low, then we're not able to see things very well. And then also what that means is that we kind of need to not pay too much attention to the fit out here. So the second order system, the fit out here is not very good. So we definitely can reject that. But the fits, the data fits that we get out here are pretty good. So this is helpful. And so what we've seen is, in the ideal case, the least squares technique works great. Least squares system identification works great. However, the technique begins to break down under some real situations: nonlinearities, quantization, noise. And we'll see how that happens. And so the question is, how do we recover a good fit using this approach? How are we able to still do system identification and obtain meaningful results, even if we have some of these things going on? So that's the practical system identification, and we'll come back and look at that next time. So this is an overview of the whole subject of system identification. It's a big subject. Thanks for watching.